Hello, class. I hope the first day of distance learning is not proving itself to be too difficult because there's so many new concepts and I want to talk about significant digits and I want to make sure that everyone is doing okay. I've decided to go through some practice questions all together. So these aren't assigned to you. But we can work on these together. So calculate, they're all from page 179 in your textbook. So number 4, calculate the number of atoms in 3.45 moles of iron. So the first thing I'm going to point out is that we have 1, 2, 3 numbers of significance. Okay. I know that some of you guys have physics background, so you'll know what significant figures and significant digits are and why they're important. We're going to just naturally get used to them as we practice more and more. Okay, so calculate the number of atoms in 3.45 moles of iron. What it's asking me to find is big N for iron. Okay, iron comes by itself, so I have this information is that I have 3.45 moles of just plain iron. It's not a molecule, it's an atom. It's all by itself. So when it's asking me to calculate the number of atoms, I don't have to do any conversion. So my formula is number of iron atoms is going to be number of moles times Avogadro's number. So I'm going to put 3.45 moles times 6.02 times 10 to the 23. And again, Avogadro's constant depends on what unit is being given to us. So the unit that has been given to us, 3.45 moles of iron, that's atoms. Okay, so I can cross these two out. And then when I multiply them, 3.45 times 6.02 times 10 to the 23, I get 2.0769 times 10 to the 24. Now, since there's only 3 numbers that are significant, 3.45, I can only put 3 numbers. So I'm going to put 2.0, I'm going to round that 7 up to 8 times 10 to the 24 atoms of iron. Okay, so moving on to number 5. A sample of carbon dioxide contains 2.56 times 10 to the 24 molecules. Okay, so in the last lesson I said everything depends on what you're reading, or the unit is dependent upon what you've read from the question. So this huge number, 2.56 times 10 to the 24, it's based off of molecules of carbon dioxide. Okay, so also pointing out we have 1, 2, 3 numbers of significance. So how many moles of carbon dioxide are present? Okay, so I'm looking for little n of carbon dioxide, which is going to be big N, number of carbon dioxide particles, or molecules, divided by Avogadro's number. So 2.56 times 10 to the 24 molecules over 6.02 times 10 to the 23 molecules per mole. Okay, so 2.56. As I put this into my calculator, I get 4.25. So that's already in scientific notation. It's a number between 1 and 9.99. And so I just have to follow significant digits. So that would be 4.25 moles of carbon dioxide. Now for B, how many moles of atoms are present? Well, the first thing we have to think is 1 molecule of carbon dioxide has how many atoms? it has 3 atoms. So it's a 1-to-3 ratio. So if I want to find the number, I'm just going to put no subscripts. So if I want to find the number of moles of atoms, I'm going to take the number of moles of carbon dioxide and then, so do you see how I put the CO2 there? I do that strategically because if you remember, I always tell you, you put what you got on the denominator and you put what you want on the numerator. What I have right now is molecules, and what I want are atoms, okay? So in 1 molecule of CO2, I have 3 atoms. And so this way I'm able to cross out CO2 and CO2, and I can see that I'm going to multiply 4.25 by 3, divide by 1. So I get 12.75. Again, I need to follow significant digits, so 12.8 moles. And here's the tricky thing. This is not in scientific notation. It's greater than 9.99, so I have to put 1.28 times 10 to the 1 moles of atoms. Okay, number 6. A balloon is filled with 0.5 moles of helium. How many atoms of helium are in the balloon? Okay, so let's think about it. We have, also let me point out, this is perfect for me to explain significant digits. All zeros that are to the left of the number, this number does not count, okay? It was not measured. All zeros to the right of a measured number, so see how 5, like clearly that's a significant digit. This 0, because it's to the right of a measured number, that is significant. However, this 0, because it's to the left, is non-significant. Okay, I know it's pretty confusing, but the rule that always got me through school is to the left, insignificant, to the right, significant. Okay, so it's asking how many molecules. So we have been given, oh, no. It's asking how many atoms of helium. So we've been given that the number of helium moles, 0.05 mole. So my formula is going to be number of helium atoms, so it's not diatomic. I'm going to take the number of moles and multiply it by Avogadro's constant. And so I get 0.50 mole times 6.02 times 10 to the 23 atoms per mole. So I'm able to cross this out, and half of 6.02 is 3.01 times 10 to the 23 atoms of helium. Okay. Okay, let's look at number 7. A sample of benzene, C6H6, contains 5.69 moles. How many molecules are in the sample? So now they're making us analyze what is actually being given to us. So this C6H6, this is a molecule, okay? The 5.69 moles represents 5.69 moles of benzene molecules. So for A, how many molecules are in the sample? We have to change this we have to convert this simply by using Avogadro's constant. So the number of benzene molecules is equal number of moles times Avogadro's constant equals 5.69 mole times 6.02 times 10 to the 23. Okay, so what is our unit on the top for this case? Well, because we have been given a number that's dealing with molecules, Avogadro's constant is molecules per mole. So let's do that in our calculator. And I get 3.5278 times 10 to the 24. Oh, I just realized up here, look, I made a terrible error. I said there's only 2 numbers of significance, and look how many numbers I put, 3. Let's change this, 3.02 times 10 to the 23 atoms. That's the correct answer, okay? Because there's only 2 significant digits here, I can only have 2 significant digits here. And see the 0? It's to the right, it counts, okay? So going back to number 7. I have how many significant digits? 1, 2, 3. So my final answer should have 3 significant digits. So I get 3.5278 times 10 to the 24. So that would be 3.53. I'm rounding that last number up, times 10 to the 24. And what is this that we are calculating? Molecules of benzene, C6H6. Okay. So then it's asking how many hydrogen atoms are in the sample. Okay, so it's asking for just hydrogen. Well, I know that I have 3.53 times 10 to the 24 molecules of benzene. Okay, so now I have to make what I got or what I want over what I got. So I have benzene, which is a molecule, okay, and I want hydrogen. So when I'm looking at this, when I have one molecule, I have to write really small, one molecule of benzene, I have 6 atoms of hydrogen. Okay, C6H6. If I have one benzene molecule, I have 6 hydrogen atoms. So I'm going to multiply that number by 6. And I get 2.12 times 10 to the 25 hydrogen atoms. Okay, I hope that this is helping clear some things up. The last example that I'll do is number 8, and then I'll leave you guys to ask me questions. Aluminum oxide, Al2O5, is that? No, it should be O3, forms a thick coating on aluminum when aluminum is exposed to oxygen in the air. Consider a sample made up of 1.17 moles of aluminum oxide. How many molecules are in the sample? Okay, so the information that they gave us, first off, there's 1, 2, 3 significant digits, but consider a sample made up of 1.17 moles of aluminum oxide. This right here is actually it's a formula unit, but who cares? What they're talking about here is talking about the whole compound. So for A, how many molecules are in the sample? I got this right from the textbook, so shame on them, they got this wrong. But we're talking about the whole compound. So I'm going to I'm calculating number of aluminum oxides equals number of moles times Avogadro's number. So 1.17 mole times 6.02 times 10 to the 23. Again, my Avogadro's constant is dependent on what unit from the question. So let's fix it. Let's change it to formula unit. Okay. Why is it a formula unit? It's because it's ionically bonded. Okay. So I'm going to multiply those together. 1.17 times 6.02 times 10 to the 23 equals 7.0437 times 10 to the 23. What's the correct answer following significant digits? There's going to be 3 significant digits, so 7.04 times 10 to the 23. Okay, So now it's asking how many atoms are in the sample. Well, in one formula unit of aluminum, Al2O3, how many atoms are there? Well, there's 2 aluminums and 3 oxygen, so there's 5 atoms. So this is our conversion. So when I'm looking at number of whatever, in this case, number of atoms, I'm going to take 7.04 times 10 to the 23 formula units. And for one formula unit, how many atoms are there? There's 5 atoms. So cross that out. And we get 3.52 times 10 to the 24 atoms. Okay. So C is asking specifically for just oxygen atoms in the sample. So I could convert using this number, okay? Or I could convert using this number, and I can show you how to do both of them. So say if I start with the first one, I want just the number of oxygen atoms. So I have 7.04 times 10 to the 23 formula units. And in one formula unit, okay, so think about it. I have Al2O3. There's 3 oxygen atoms. And so when you multiply that together, you get what? 2.11 times 10 to the 24 formula units. Oh, no, not formula units. Atoms of oxygen. Do you see how oxygen isn't diatomic there? It's because I'm talking about individual oxygen atoms, not oxygen in the atmosphere, not oxygen existing by itself. The aluminum and the oxygen, they exist in an ionic compound, and I'm just looking at the oxygen that's in that ionic compound. I'm not looking at oxygen by itself. Say if I heated up the aluminum oxide and I said how many molecules of oxygen are produced from heating it up. Well, when you separate the oxygen from the aluminum, then oxygen goes back to being diatomic. But for right now, when it's in a formula unit, when it's in a molecule, and you're talking about atoms of oxygen, they just exist by themselves. Okay, say if I took the answer from B. So number of atoms is 3.52 times 10 to the 24 atoms. Well, for every 5, for every 5 atoms, okay, so think about Al2O3. There's 5 atoms that we use to convert, and 3 atoms of those 5 are oxygen. So for 5 atoms, 3 atoms are oxygen. So again, you're always putting what you want over what you got. And so I'm going to take that number, 3.52 times 10 to the 24, times 3 divided by 5, and I get 2.112 times 10 to the 24. I get the exact same answer. I'm glad I did that mental math right, otherwise that would be very embarrassing. Okay, so hopefully that helped. I know that some of these can be confusing. Let me know if you need any help. I can see people slowly submitting your work. Thank you very much. I can see how dedicated you are. If you need more explanation, if there's a concept that you don't understand, let me know. I'm happy to do these.